Hello everyone. I wanted to talk a little bit about oxidation reduction reactions. This is a review. This is something that you should have covered in Chemistry 1A. For your textbook, it should be at the end of Chapter 4. If you have the most recent edition, it's possible that will be a different chapter. So just look for oxidation reduction in the table of contents. And the first chapter you see with that is the chapter that you want to read to touch up on the subject. All of chapter 19 is about oxidation reduction. So that's why I wanted to make sure we have a good basis of understanding this, what we learned in Chemistry 1A, before jumping into kind of the deep end on when we return to live lectures. So you do want to make sure you feel comfortable with everything we talk about in here, because we're going to be taking these ideas and then extending them and applying them to more complex ways of looking at this kind of reaction when we get back to the live lecture. So a redox reaction is a reaction in which electrons are transferred from one atom to another atom in the reaction. Sometimes we call these redox reactions for short. There's a part of the process that's an oxidation, a part of it that is a reduction. These two always go together. You can't have one without the other. You can't lose electrons without those electrons going somewhere else. So we say that if an atom loses an electron, that it is oxidized, and that if an atom gains an electron, it's reduced. Now, those two sentences kind of on their face might seem contradictory. So we're saying losing, we're saying gaining is reduced, not losing is reduced. So that might seem a little bit backwards. You definitely want to make sure you have this correct, so you know which one goes together. So losing electrons is oxidation, gaining electrons is reduction. You need to make sure you know that and be able to apply that as we go through this. There are a couple of mnemonic devices that can help with this. One is the phrase oil rig. So oxidation involves losing electrons. Reduction involves gaining electrons. So that's one. The other one is Leo the lion says grr. So LEO, lose electrons oxidized, GER, gain electrons reduced. So those are kind of silly, but if you need something silly to help remember chemistry, that's fine. So we have an example here of a reaction that is a redox reaction. So we can see in the reaction that we're showing here, the sodium atom is losing an electron. So that's an oxidation. We see it losing as we go from a neutral solid to an ion, with a +1 charge. So that is a loss of an electron. The chlorine, on the other hand, we can see is gaining an electron. It's going from the elemental form, which is stable, to a chloride with a -1 charge. So it has an additional electron there. So we want to be able to look at a reaction, know when we have a loss or gain of electrons. So here we're again talking about these different processes. So oxidation, we're losing electrons. Don't worry too much about the oxygen hydrogen stuff. That's something, if you go on to take organic chemistry, you'll learn that part in more detail. The oxidation numbers, we'll be looking at how we determine what those are here in a minute. And half reactions are what we'll be looking at in class. So those are kind of a big deal. We are not going to get that far today. Okay, so I want to talk about these oxidation numbers. The oxidation number is a form of bookkeeping to help us keep track of whether or not we have our redox reactions. We're looking at kind of this assumption that we are completely transferring electrons. That is not true. We don't always have a complete, sometimes we do have a complete transfer, but we don't always have a complete transfer of electrons. But by using this method, we're able to determine if it is happening. So the main point of this method is once we have oxidation numbers, we can see how they change, and as they change, we can then use that change to determine with what is oxidized and what is reduced. Okay, so just a little bit about the assumption going into this term oxidation number. Okay, so we're going to go through the set of rules. You probably saw this in Chem 1A, so this is hopefully a refresher for you in terms of what these are. So any element by itself, any free element has an oxidation number of 0. So in the example we just saw, the sodium metal, the chlorine gas both started at oxidation numbers of 0. Here are some additional examples. You'll notice that they can be as a molecule, or they can be in some other form. So the form itself doesn't matter as long as it's all by itself. Oxidation number is 0. If you have an ion, if it's a monatomic ion, the oxidation number is simply the charge of that ion. So hopefully that is pretty straightforward. So a couple of examples here. Could be plus charges, could be minus charges. So anytime you see an ion, you know what the oxidation number is. When we have a molecule or compound, I guess I should say when we have a compound, the oxidation numbers have to add up to 0 within that compound. So whatever they are, they have to add up to 0. We're looking here at water as an example. So whatever the oxidation state of hydrogen is, we have 2 of them. We have 1 oxygen. Somehow that adds up to 0. We'll get to figuring out how that works a little bit later. But essentially, if you know one of them, you can use this to figure out the other one, is how that will typically work out. Additionally, if you have a polyatomic ion, the atoms in that ion will add up to the charge of the ion. Okay, so here we're looking at the nitrate ion. So we have 1 nitrogen and 3 oxygens. Whatever those charges are, I'm sorry, I should say whatever those oxidation numbers are, they add up to a -1. So again, if we know one of them, we can use that to figure out the other one. This is similar to number 2, but it's a little bit more specific. So if you have a compound with a group 1 or group 2 metal, we know that they will be +1 or +2. So that's always going to be true. You would have probably assumed that it will be true. So +1 and +2. Okay, some additional ones we'll see on this table here. And we'll refer to that here in a minute. Okay, so referring to this for the nonmetals. So a little bit about this table. If you look on the table itself, there shouldn't be anything that's really that surprising. These oxidation states match what we would expect for charges if these were present in ionic compounds. What I do want you to pay attention to is the order. Okay, so the order here does matter. The thing that is higher on the list has a higher priority. So fluorine has the highest priority. Fluorine is always a -1. Hydrogen is a +1, almost always a +1. What is the exception? If it's with fluorine. So fluorine has a higher priority than hydrogen. Hydrogen has a higher priority than oxygen. So if oxygen is with hydrogen or fluorine, it won't necessarily be a -2. And then we work down the list. So the halogens, the rest of 6A, and then 5A. Most of the time, it would just be one of those top 3 that's changing anything that is below it on that list. Some of the ones that are lower on the list could change things that we're not showing on the list at all. And then the final one is basically just telling us how to make sense of these. They will sometimes contradict. For example, hydrogen, fluorine, if they're together, they can't, actually they would work out together. That's not an exception. But it's possible that oxygen, fluorine wouldn't work out, or oxygen, hydrogen might not work out in some cases. So we follow these rules in the order that we're listing them here. So when you get to number 5 is when you kind of have to start applying some of these ideas. If we are not covering it in one of these, so in 4 and 5, then that's when we go to rule 3. So rule 3 is, okay, we know they have to add up. How does that work? Well, look on the list for 4, look on those list for 5, look for one of those things on that list. You then know what that one is. That helps you figure out what the other one is. So we go through these in order. There's some examples of this, again, in your textbook. This is giving some page numbers. Again, depends on the edition you have, if those would be correct. So just look in your book for some examples of this in the early chapters. I do want to go through some examples here, though, as well. It says assign oxidation numbers to all the elements in the following compounds and ion. So we have 2 compounds there and an ion. What I would like you to do if you're watching this video right now is to pause the video, and then try to solve each of these 3. And then once you've done that, come back and we'll go through the answers, and you can see if you're on the right track or if you need a little bit more practice. Okay, so let's go ahead and look at the answers for these. So the first one, we had lithium. I think it was lithium and oxygen, right? So Li2O. So we can see rule 2 tells us that lithium is a +1. That's exactly what we would expect. Oxygen is a -2 according to rule 5. Fortunately, those two don't contradict each other. So +1 and a -2. If they did contradict, we would go with the lithium. So we have 2 lithiums, each a +1. That means the oxygen has to be a -2. The whole thing adds up to 0. So the next one, let me just go back and remind myself, we had nitric acid, HNO3. So here we have 3 different elements that we have to somehow balance out. So hydrogen is the highest one on that list for table 5. So it will be a +1. And then then we have nitrogen and oxygen. We could think of that as hydrogen ions and the nitrate ion, or we could think of it as 3 separate things. We could do that either way. So between nitrogen and oxygen, oxygen is higher on the list, and it is a -2. So we assign oxygen a -2 for its oxidation number. And then with the number of oxygens and nitrogens we have, that needs to add up to a -1. So we can see we have 3 oxygens. So 3 times a -2. So each oxygen is a -2. And then we're basically doing some algebra here where we're calling the oxidation state of nitrogen X. So X plus the number of oxygens times the oxidation state of oxygen adds up to a -1. So that will give us, give us a -6. So X has to be a +5. So that's the oxidation state of nitrogen in this compound. Now, is that a charge? It's not a charge, it's an oxidation state. And what we use that for is when we see that number change, we'll know that we have a redox reaction. So it's a big number, so we would expect it to maybe go down in a reaction. We'll look at some reactions here in a minute. Okay, so there's one more. So let's go back and we see that this one is an ion. We don't even have the pretense of having a hydrogen there with it. So it has a -2 charge altogether. Cr2O7, 2-. Let's go ahead and talk about that. So here we see, so this is called the dichromate ion. Here we see that we have to apply rule number 6 to figure out the chromium. Oxygen, again, -2. That's going to come up a lot, oxygen being -2. So we do something similar to what we did up here. In this case, though, instead of a -1, we have a -2. We have 7 oxygens. And we also have 2 of this other portion of the substance. So 2 chromiums, whereas in B we had only the 1 nitrogen. So we have 2 times the number of chromiums plus 7 times -2 for oxygen. All of that adds up to a -2. So if we do the math there, so 7 times minus 2 is a minus 14. We move that, we add, so we would add 14 to both sides, so we would get a 12. So 2y equals 12. Divide by 2, we get y equals a plus 6. If that seemed kind of fast, you might want to write out the algebra steps to get there. Okay, so a couple examples here of assigning oxidation numbers. These are fairly typical types of molecules and ions that you could see. You want to be really comfortable doing any of these before we meet in class to start into chapter 19. Okay, one more example here. In this case, what we're going to be doing is not only assigning the oxidation numbers, but then from that information determine what's oxidized and what's reduced. So it's very similar to what we just did, except for each one you're going to have not just one substance where you're assigning numbers, you'll have several, and then once you do that, you do a comparison. So again, go ahead and pause your video. Try to do each of these, and then you can play it and see how well you did. If you want to just try the first one first, and then see the answer before going on to the second two, that's fine as well. But I do want you to practice it before I tell you what the answer is. Okay, so let's go ahead and look at the answer. So for the first one, we had nitrogen by itself, oxygen by itself. Each of those will be have an oxidation number of 0. For the nitrogen, though, if we go back, we have nitrogen into O. So we have over here, we have oxygen has a higher priority, so it's a -2, so we're familiar with that. Then nitrogen would be a +1 because of that. So applying those oxidation state rules. So we go from a +1 to a 0. It's by itself. Oxygen goes from a -2 to a 0 by itself. Okay. So that's assigning those oxidation numbers and seeing how we change those. So nitrogen went from +1 to 0. Well, oxygen went from -2 to 0. So the nitrogen is oxidized, the oxygen is reduced. Okay, so again, you want to remember how to know what's oxidized, how to know what's reduced. Let's look at the next one. So we have lithium and nitrogen are the two reactants. Those are both elements by themselves. They will be zeros. If we come to the product side, we have Li3N. Lithium will be +1 here. We have 3 of them, so nitrogen will be -3, and that makes sense for nitrogen. So we can see we're going from 0 to +1, 0 to -3. Okay, so we're showing that here. So the lithium is oxidized, the nitrogen is reduced in this case. Okay, so one more. Here we have a lot going on. It looks a little bit more complicated than what we saw before. I'm going to tell us how we can simplify this a little bit. We don't have to assign every single thing here because we'll notice that the nitrate here and the nitrate here are the same. They're the same thing. They are not going to change. We don't have to worry about, okay, oxygen is a -2, nitrogen is a +5. We've already figured that out in a previous example, but we don't have to worry about that here because it doesn't change. If we saw nitrogen over here somewhere else or oxygen somewhere else, then that would be very important to do that. If the polyatomic ion is not changing, then we don't have to assign it. Okay, so what we can do is we can say this is a 0 for the nickel. For the lead, nitrate has a -1 charge. There's 2 of them. So this is a -2. So the lead has to be a +2. On this side, the lead is 0. And again, 2 - 1. So the nickel is a +2. So that's how we can assign oxidation numbers there without getting into too much detail on those polyatomic ions, which are basically spectator ions. Okay, so nickel went from 0 to +2. Lead went from +2 to 0. So the nickel is being reduced and the lead is being oxidized. This specific type of reaction where we have two metals, where one is a solid on one side, one is a solid on the other side, this is probably one of the most important reaction types for chapter 19. We'll see a lot, we'll be looking a lot at this very specific type of reaction. Not necessarily nickel and lead, it could be other combinations of metals, but that process, that's the one you're going to have to be really good at identifying oxidation and reduction for. So again, if you want to find more examples of that, if that wasn't clear in your textbook, make sure to do that before coming to class. Okay, so just the summary of oxidation reduction reactions. We have a transfer of electrons in these reactions. So here we're showing this reaction where we have magnesium reacting with oxygen. Again, two elements initially, and then they form a compound. The magnesium is forming magnesium ions, so that's an oxidation. And the oxygen is forming oxide ions, so that is a reduction. So we have part of it is losing electrons, part of it is gaining electrons. We're basically breaking this into two halves, so we call these half reactions. The magnesium half reaction, oxidation, the oxygen half reaction, reduction. Where we're going with this when we get back to class is we will be looking at how we can break more complicated reactions apart into half reactions to then figure out a lot of the details going on with them. Here we're showing putting those half reactions together. The electrons will cancel out. So we're just taking the reactions we wrote and putting them together. The electrons will cancel out. We get the overall reaction. That is essentially what we're going to do in class when we get back to class. The difference is we're going to have more complicated reactions than this one, where we might have other things showing up as well. So that is the review